In the field of artificial intelligence, systems frequently process millions of individual data points. Since it's impossible to analyze every single point manually, we use summary statistics to capture the overall characteristics, or the baseline average of a data set. This allows an AI system to establish what is considered normal behavior, handling all that data so it can effectively identify anomalies or outliers. To understand these concepts intuitively, let's consider an analogy: a quality control manager at an iPhone battery factory. Our manager here needs to know how the factory is performing overall without testing every battery themselves. First, we have the mean, which is the mathematical average. It's calculated by adding the lifespans of all batteries produced together and dividing that total sum by the total count. We often call this the fair share average because it distributes the total value equally across the entire group, giving us a representative average life, like 10 hours. Next is the median, representing the exact middle value. To find it, we take every battery and line them up in order from the shortest lifespan to the longest. The median is simply the value sitting in the dead center. Then we have the mode, which is the most frequently occurring value. If we sort our batteries into bins based on their lifespan, the bin with the most batteries, say the one with exactly 10 hours, is our mode. It's simply the most common result. Now, why do we need both the mean and the median? It comes down to resistance to outliers. Imagine you are in a room full of middle class individuals. If one billionaire suddenly arrives, the mean wealth in that room would drastically increase, skewed heavily by that one extreme value. However, the median would remain largely unchanged. Therefore, the median often provides a more accurate reflection of the typical person when extreme outliers are present. Finally, we need to measure how reliable our factory machines are using variance and standard deviation. These metrics capture the spread of our data. If the battery lives are highly inconsistent, with some lasting 2 hours and others 20 hours, the standard deviation is high. This creates a widely scattered, unpredictable distribution. Conversely, if our factory is highly consistent, producing batteries that all last right around 10 hours, the standard deviation is low. This indicates a precise and tightly grouped and predictable process. To summarize our anchor takeaway, the mean calculates the mathematical average, the median finds the middle of a sorted list to resist outliers, and the mode identifies the most common result. Let's move on and look closely at the exact mathematical steps we use to calculate that spread, specifically focusing on variance and standard deviation.
Following up on how we establish a baseline of normal behavior, we need a way to measure what is normal versus what is an anomaly. We do this by looking at the spread or dispersion of our data. Imagine your data points plotted along a timeline or a ruler. Right in the middle is your mean, or the center of gravity for your data set. The physical distance from this center mean out to each individual data point, like this point here or this one further away, represents our overall data spread. To actually quantify this spread mathematically, we calculate a metric called variance, which is denoted by the symbol sigma squared. Let's walk through the 3 steps to calculate it. First, we take an individual data point x sub I and our mean mu, and we subtract the mean from the data point to find its deviation. This tells us exactly how far that specific point is from the center. Second, we square each of those deviation results. Why do we do this? Because some points fall below the mean and yield a negative distance, while others are above and yield a positive distance. Squaring them ensures all our values become positive, so they don't just cancel each other out to zero. Third, we find the average of those squared values by summing them up and dividing by the total number of points n. The resulting number is our variance. But there is a practical problem here. Because we squared the numbers during our calculation, our variance ends up in squared units, for example, squared hours of battery life. That is really unintuitive to interpret. So to fix this, we simply take the square root of the variance. This gives us the standard deviation, denoted as just sigma. Taking the square root is vital because it brings our measurement perfectly back into the original units, like regular hours. Let's pull this all together by looking at the mathematical formula at the bottom. Here is the complete equation for standard deviation. In this formula, sigma represents the standard deviation, which is the total spread. Inside the giant square root, we take each individual data point minus the mean and square it. The large sigma symbol here tells us to sum up all those square deviations. Then, we divide that massive sum by the total number of points n. Finally, applying the square root over the whole fraction gives us our final usable number. To summarize the core takeaway, variance measures the average square distance from the mean, and standard deviation is its square root, representing the spread in original units. Next, we will look at how the standard deviation visually shapes our data into a familiar mountain-like bell curve.
We just learned how to calculate variance and standard deviation mathematically. Now let's see what that actually looks like visually. When we plot our data, we often see this shape, commonly referred to as a mountain or a bell curve. To understand what we are looking at, let's check our axis. The horizontal axis represents the actual value of our data, while the vertical axis represents frequency, which is just a fancy way of saying how often those specific values occur in our dataset. Now look at this dashed line right down the middle. This marks the absolute peak of our mountain. In a perfectly symmetrical distribution like this one, the center line is exactly where the mean, median, and mode all align perfectly. Because everything balances perfectly around this point, you can think of it as the center of gravity for your entire dataset. But how does standard deviation actually affect this mountain? Standard deviation physically alters the shape of the curve. Let's look at the bottom left. If we have a small standard deviation, our mountain looks very tall and skinny. Why does this happen? Because almost all the data points are very similar to each other. They are huddled tightly very close to the center average. On the other hand, look at the bottom right. If we have a large standard deviation, the curve stretches out and becomes much wider and noticeably flatter. This happens because our data points are highly scattered. Instead of being clustered together, they are spread out far away from the center. The key takeaway here is that the shape of the curve instantly tells you how spread out your data is. A tall, skinny curve means your data is tightly clustered, while a flat, wide curve means your data is highly scattered. Now that we understand how to visualize this, let's explore how automated systems use these exact shapes to make critical decisions, like detecting fraudulent behavior. These statistical tools are applied across various industries to make automated decisions. In the banking and financial services sector, an AI monitors your average monthly spending, which is the mean. It also calculates the standard deviation of your spending habits. Let's say you typically spend around $1,000 with a standard deviation of only $200. A sudden transaction of $5,000 is instantly recognized as being many standard deviations away from your norm. This triggers a fraud alert because the behavior is highly unusual. Next, look at e-commerce, specifically at Amazon, where statistics are used for inventory management. They calculate the mean number of iPhones sold daily to understand general demand, but they must also account for sudden sales spikes, such as those occurring on Fridays. By looking at the standard deviation, they can calculate safety stock. This ensures they have enough extra units in trucks ready to go to cover the fluctuations or spread in demand. To calculate these values in a professional environment, developers use libraries like NumPy in Python. Consider a list of delivery times for a logistics company: 3, 4, 5, 4, 3, 4, 10, 4, 3, 2. The code first uses np.mean to find the average, which results in 4.2 days. Next, np.median identifies the middle value. Even with that slow delivery of 10 in the list, the median remains 4.0, showing it is much less affected by that outlier. Finally, np.std calculates the standard deviation, or spread. A higher number means unpredictability, while a lower number shows consistency. To solidify these concepts, let's look at three practical applications. First, salary skew. If a boss earns $1 million and the employees earn $50,000, the mean is skewed way too high. The median is a better typical number here because it ignores the outlier. Second, if the standard deviation of a machine's output is zero, it means there is no variation at all. Every item produced is perfectly identical. Third, for a shoe store deciding which sizes to stock, the most useful statistic is the mode. The store needs to know the most requested size from real customers, not an average size that might not even exist. By mastering these summary statistics, you can now take a massive dataset, run it through these tools, and reduce it to just a few meaningful numbers that perfectly describe its center, its consistency, and